Welcome back. In the last lecture, we have seen how distance protection works. Now let us try to apply the distance protection protecting your transmission lines. Okay. So when I come to this transmission line, transmission lines are basically this. They are spread over some I'm just ignoring the transformers. So they will be connected. Transmission lines are connected between generators and the loads, and they will be transmitting the power over very long distances, sometimes in thousands of kilometers also. So when they are spread over very long distances, then it is difficult for us to incorporate so many protection systems. We cannot measure the things everywhere. So in that case, distance protection offers us a very big advantage. So you keep the distance relay here, and based upon the protection, based upon the current and voltage measurements, you can take a decision. Now you can ask me that why don't we use overcurrent relay? Because if there is any short circuit, then automatically an overcurrent relay will be helping you out, right? Yes, this is a very good question. How overcurrent relay is not employed? Why overcurrent relay is not regularly employed? You can employ overcurrent relay also, but the problem with the overcurrent relay we have seen in the last week. We need to choose characteristics, we need to choose operating TMS, we need to choose PSM, etc. etc. And moreover, the overcurrent relay operates a little bit slower when compared to your distance protection. So distance protection, as already said in the previous lecture, it is very fast. It just only measures voltage and current and then just takes a ratio and compares it. So it is a little bit faster when compared to the overcurrent relay. So the first thing is operating current. The second thing is, in case of an overcurrent relay, you need, as already said, you need to have some settings of TMS and PSM, plug setting multiplier, etc. etc. So many things will be there. In case of distance relay, you don't find any such sort of readjustments or anything. It will be having a permanent setting. It will be just measuring your voltage and current, and based upon that, it will be giving you measurements. So a permanent setting is advantageous all the time when compared to every time adjustments. So that's why distance relay is protected. And the biggest advantage is that because they only take the calculation of V and I, they will just only measure the things. They will just take the ratio. So that's why their fault current magnitude permits very high line loading also. This is one of the biggest things. And this distance protection relay, this is distance, it is having a less effect on the amount of generation and fault levels. So this I'll explain in theory class why I have written this one. Normally, in case of generation and fault levels, your distance relay acts very better when compared to your overcurrent relay. Why and how we will see in the class. Okay. So because of these advantages, overcurrent relay is generally, it will be included in all of the things. Distance relay is given more preference when compared to the overcurrent relay. Normally with the modern day numerical relays, your computer is performing all the operations, so you need not bother about whether to implement an overcurrent relay or a distance relay. In olden days, we used to have a distance protection, but nowadays, you are measuring voltage and current, you give it to a computer. Your computer will decide whether it can act as an overcurrent relay or a distance relay or a differential relay, whatever it might be. So nowadays, it is not a big problem. But in olden days, distance relay was preferred when compared to the overcurrent relay. Now, particularly in three-phase systems, still if you are employing conventional or analog distance relays, generally they are employed either for, as already mentioned, they can be employed for primary protection and also they can be employed for backup protection also. So they are used for protection of transmission line and distribution lines, particularly against three-phase faults, phase-to-phase faults, and phase-to-ground faults. Triple L, triple LG, double L, These are the different types of faults which you see in transmission systems, right? Which involving three phases, which involve two phases, which involve only a single LG faults. Okay. So any of these faults you can protect your transmission systems using distance relay. Okay. So now, as already mentioned, a quick review of your operation of your distance relay. As already said, it is a double acting relay where it consists of two coils. One coil is basically energized by the voltage, the other coil is energized by the current, and both coils they will develop a torque. One will develop a positive torque, one will develop a negative torque. The torque is produced in a way that when the V by I reaches below a set value, then the relay will operate. So when a Z is less than a Z set value, then the relay will automatically operate. In case if there is any fault in the transmission line, automatically what happens? See, what is this Z? V by I, right? In case if there is any fault, automatically I will be increasing and V will be decreasing. Right. So in that case, if it is decreasing and if it is increasing, then automatically your Z value will be decreasing, right? So if it falls beyond your setting value, then automatically your relay will operate. So this happens for every short circuit faults. So the voltage at which is at the VT location is dependent on the distance between the VT and the fault, isn't it? So that's why the name distance protection has been given. So if the fault is closer to the relay, then the measured voltage will be very low. As already mentioned, let us suppose this is your transmission line. This is your CT which you are measuring here, and this is the fault, and this is the current which is flowing. So automatically what happens? The VF is equal to IF into Z plus whatever the length of the transmission line which are concerned. If the fault has occurred far more at a very farther place when compared to the location of your PT, then automatically what happens? The transmission line length will be increasing. So is the impedance. So automatically the voltage measured will be a little bit higher. So if the fault is nearer to your PT, then V will be a little bit low. So automatically what happens? If V is low, then automatically Z will be low. Then you can automatically identify the fault. The distance relay will quickly identify the fault. If it is far enough, then there is a difficulty for identifying the faults. So it is completely depending upon the distance. Okay. So based upon the distance, the impedance will be there, right? So the transmission line impedance is proportional to its length. So we can use the distance relay and we'd operate the faults that occur in between the relay location and the predetermined points. So I'll set this distance protection up to this one. Beyond this, it won't operate. But sometimes what happens is this region will be neglected, which we call it as a reach. That I think you might have already studied. So that's fine. To overcome these things, what we do is nothing but we will employ 3-zone protection. Okay. Now, before I go with this, let me before I go for this, let me tell you about how to implement a numerical distance. So how it will be implemented? See, I'll just give you the important steps. The first thing is, you read the values of the currents and also the voltage, and you read the values of setting value of your relay. These things you should get before you start the operation. Once you have these values, once you do have this, these will be samples. You will be getting a large number of samples, in particular in case of numerical relay. Okay. So your ADC converters, they will be giving you a large number of samples. So from I samples, you calculate fundamental components. You calculate RMS value of the fundamental components. RMS value of fundamental components, which we call it as I1 RMS. And from V samples, you calculate RMS value of fundamental component. Again, this time it is V1 RMS. Now once you do have it, now you measure Z, which is equal to V1 by I1 RMS. The next thing is you compare with setting value. If Z is less than Z set, then automatically what happens? You will give you the trip signal. So, if Z is greater than Z set, then what will happen? Read the samples. Again, you extract the thing, which is nothing but going back to step number 1. Understood? So, better you take this one high and next you take this one, because Z set value will not be changing unless you require. Normally, what they will be changing is the samples only will be changed. So, this one you take up, this one you take as a second one. Okay. So, and if you feel that Z is less than your Z set, trip the signal and then you stay silent. Okay. So, this is how you should implement a numerical distance limit. Now, let's see how a flowchart can be drawn for this. Start. Read Z set. Now, read V samples and I samples. You calculate IRMS of fundamental components. You can choose any of the techniques, because we have seen in unit number 2 there are so many techniques if you do have. The derivative methods, you can have the sample techniques, 2 sample, 3 sample, the first and second derivative, the fundamental and the first derivative. You can have the Fourier series, you can have the Walsh series, you can have the wavelet analysis. Any of these methods you can employ to determine the fundamental component, RMS value of the fundamental component. And then you calculate VRMS of the fundamental components. Again, what you will do, you will calculate Z, which is equal to VRMS by IRMS. Now, what you will do, you will check with Z by units, then automatically what happens, you will give the trip signal is to be issued, and you will stop the process. This is for yes. If it is no, then you will go back to your, this is the way. Now let us suppose if you want to include a time delay component, which means you need to wait. If you want to wait, if you are in the backup protection, then automatically what you are supposed to do, even if you measure it, you need to provide a backup, right? So in that case, see this particular phenomenon, I'll show you. If Z is less than ZPU, yes, wait till delay time. Again, what you do? Again, you read the samples. Again, you measure IRMS, VRMS, and Z. And then again, now you do another checking here. If Z is less than ZPU, then you will set the command. Here it will go. And then stop. If no means, then this is the case. Understood? So this is, in this way we will be trying to implement the numerical layer. Right? So now you are supposed to write a program now. What you are supposed to write a program? You are supposed to take input from the user, the Z set value. This will be fixed most of the times. The next thing is you need to take the samples, the number of samples which you will be getting, because here nowadays PMUs are there. PMUs will be giving you signals all the time with the GPS stamping. Now from the samples which you do have, you are supposed to calculate these things. You need to write a code, software code. And then you need to write another code for determining VRMS. Both will be the same, only the samples will be changing. Once you do have these things, you will be calculating these things. Next, a decision making if loop, and then you will be giving the signal outputs. Right. So if you write it in a Python code, so the first thing is V is input, sum, enter samples. I input, enter samples. If it is just like an array, then what you are supposed to do? You are supposed to use a for loop, right? And Z setting inputs. So these are the things which you will be taking from the user. Enter impedance setting. Once you do, you will calculate VRMS. How? There is a procedure, right? We can employ any of these. Next, we will be calculating IRMS. Next, we will be calculating Z. How? VRMS by IRMS. Now, you will write if Z is less than Z per unit. What will you do? Printf. Strip the signal. Else, what you will do? You will again V is equal to again inputs. V is equal to again, I is equal to again input. The same story will be started again. Okay, so this process will be repeating again and again till you find a trip signal. If it is a trip signal, then automatically your relay will go to the idle state and the circuit breaker will operate the system. Okay, so this is the way how a programmer is supposed to write a logic. So I have given you a flowchart. You can develop a pseudocode. You can write a program in any of the programming languages. As already I mentioned many times in the class, it's a time for you to step up and write the programs. Nobody is using electromechanical LS nowadays. The future is all about numerical LS, and we do need programmers, good programmers. You should think the logic, develop a flowchart or a pseudocode, learn a language, implement that flowchart. Using that flowchart, you should write a program. Okay, so with this, I'll be closing this concept of numerical distance protection. And in the next lecture, we will see the Mann and Morrison method of how to calculate the fundamental component of the current and also the voltage. Okay.